Hello and welcome to another lecture of classical motion of a single particle. Before we discussed various features of Newton's laws and how directly starting from a simple Newton's law, we can, depending on the various type of forces, we can encounter different situations. And also we have discussed different conservation principles. We have said that if the net force is 0, if the force is 0, if the external force acting on a particle is 0, then the total linear momentum is conserved during the motion. Okay. Then we also said that if the torque is 0, then the angular momentum of a particle is conserved during its motion. Then we said that if the force has a specific property that it can be written as a gradient of a scalar function, then this force can be called as a conservative force, and under the action of a conservative force, the total mechanical energy of a particle remains conserved during its motion. In the last lecture, we also showed that how it is, how one can necessarily and sufficiently claim that if a force field has 0 curl, then it can be written as a gradient of a scalar and vice versa. Now, in today's lecture, we will discuss a very important concept, that is the concept of equilibrium. Very often whenever I meet students or scholars in formal interviews, talks or even informal discussions, and the word equilibrium is used, I see that very often students use this concept that equilibrium means potential energy is minimized. Now, of course, I am not saying that they are wrong, okay, but the concept of equilibrium is much more general. So, it also depends in which framework you are talking. So, in the framework of classical mechanics, what is the exact meaning of equilibrium? That is the main content of this class. So, equilibrium does not say an unperturbed state of motion. Whenever we are talking about equilibrium, it is a state of motion which is equivalent, or I would say identical to an unperturbed state, but the reasons, but the agents of perturbation remain present. What is the meaning of that? The meaning is that if you have a system of, let us say in classical mechanics, if you have a particle which is moving, let us say under the action of some force F, let us say in this direction, then of course you know, due to Newton's first law and second law, this particle will be accelerating. Okay? That means this particle will be subjecting at every instant of time to change its state of motion. Okay? So, and actually also you know, for a particle with constant mass, it is even simpler, that is m times dv dt will be exactly equal to F. But now, if I say that I have a force in addition to this F, I have a force which is F prime. So, if the attempt of this force is to pull or to lead this particle exactly in the opposite direction of this force, and if magnitudically these two forces are same, that means F mod is equal to F prime mod, then we can actually say that F is equal to vectorially minus of F prime, and F plus F prime is equal to 0. So, this is a condition where you see that although the particle is subject to two forces, the particle, I should write with a blue one, the particle is subject to two forces F and F prime. That means the particle state of motion is perturbed. State of motion is perturbed, or actually there was an attempt to change the state of motion of the particle. In this situation, only because the effects of those two perturbing agents are exactly balancing each other, equal and opposite. So, equal in magnitude and opposite in direction. That is why vectorially the net effect of the force vanishes. So, whenever you encounter in nature a situation where a particle or a system has many, or at least more than one perturbing agents, but those perturbing agents somehow in some situation balance each other to create a state which looks like its unperturbed state, then the equilibrium is defined. Then only the equilibrium is defined. If a system just right from the beginning, I do not disturb it at all, then the system is in its initial state, then we do not talk about equilibrium. Okay. Equilibrium means that there is some effective perturbation which has been made, or there was at least some effort of perturbing the system by more than one agents, and somehow if you now destroy the balance of one of those agents which are balancing each other, actually you will see that the system is not in actually an unperturbed state. So, you will actually see the real picture of the system which is undergoing some attempts of perturbation. So, in the first case this is so whenever there is no force at all, a particle is not moving or it is always moving with uniform velocity. That is the Newton's law. Okay. In this situation we say this is an unperturbed state. Now, whenever we talk about equilibrium, we actually think of a compromised unperturbed state, but once you do not agree to compromise, that means all the forces are not exactly balancing each other, all the effects are not balancing each other, then again you have non-equilibrium states. Okay. So, now you can generalize the concept of equilibrium. So, for equilibrium, I am just writing, for equilibrium F plus F prime should be 0 and can be in general, this is true for any number of forces. So, I can start with F1, F2, F3. This. Okay. Here we are talking about forces only because in the framework of particle dynamics, we have the force as the only known perturbing agent, okay, because that causes the motion, that causes the change of state of motion. Okay. So, if we have this condition, then you have equilibrium. But of course, if I now say suddenly I have realized that I do not want to put this force, I somehow remove, or the agent which is exerting this force, or let us say some another force, let us say F1 for example, the agent withdraws the force, then suddenly you will see the total summation of Fi will no longer be 0, if let us say F1 is 0, then suddenly. So, basically when we are talking about this 0, so this is just making the vector sum of n vectors to be equal to a null vector, and you can actually think that none of them are actually 0. So, no Fi is equal to 0. Now, if I say that this F1 is actually 0, then suddenly you will have this situation where I will be equal to 2 to n, and that will be your non-equilibrium state. That is the most general concept of equilibrium in classical mechanics. Now, the point is that where we in general encounter such type of things. So, a very important consequence of the equilibrium is that, let us say in your system you have more than, let us say you are talking about one particle which is moving in a conservative force field. Now, we know that the total mechanical energy of that particle will be a constant in time. Now, let us say I am starting by some external agent a force which is proportional to V. And we talked in a previous lecture that proportional to V, a force proportional to V always introduces a dissipation, that we actually showed. If we have that, then you will see that due to the introduction of this dissipative force, your total mechanical energy will no longer be constant. However, if you make the dissipative force to be vectorially equal and opposite to the conservative force field, the net acceleration of the particle can be made to be 0. So that it may appear that the particle is actually having no force, but this is not true. So, you will now actually see with this very simple example. Let us say you have a particle, and Newton's law in general for that particle is this. Now, let us say this particle is moving under a conservative force field with potential phi. So, the force field should be minus gradient of phi. You know what is the immediate conclusion from that, that is half mv square plus phi is constant in time, ddt of this is 0. So, if I write ddt, I have to make 0. Okay. Now, if I add, I just take another color a little bit different, yeah. If I now add, if f external is equal to minus of grad phi minus of alpha v, where alpha is greater than 0, then what happens? Then you will have m dv dt is equal to minus gradient of phi minus alpha v, and you can simply do the trick v dot everywhere, and you can actually show that ddt of half mv square plus phi is equal to minus alpha v square, and which is of course less than 0 because alpha is positive and this is also positive because it is a square quantity, right. So, you see that when this particle had no force on it, the particle was moving of course without acceleration. So, dv dt is equal to 0, but its total energy, which was nothing but the kinetic energy, was conserved in time. That you can show easily just by taking m dv dt is equal to 0. So, v dot m dv dt is equal to 0. So, we say this is a case of a free particle. Okay. Then we say half mv square is constant in time. That is nothing but, this quantity is nothing but ddt of half mv square. Okay. Now, if you have this case where you have two forces minus, so I use the highlighter, you have minus grad phi and minus alpha v. Yeah, this is the conservative one, conservative, and this is the dissipative. Then you will see again you can make a situation where this dv dt is equal to 0. Here also dv dt is equal to 0 if minus gradient of phi is equal to alpha v. So, this is a possible case, but Is this the case exactly like the free particle? Of course not, because you know now its total energy, which was constant half mv square plus phi, it is no longer. So, what I am saying, the message, the very important message of this is that to conclude whether two states, that means the unperturbed and state under equilibrium, are same or different, it is we have to check dvdt, of course, that is the dynamics, but also as well as the conserved quantities. So, to be very honest, when this dvdt is 0, this case is dynamically equivalent to this, but energetically this state is not equivalent to a free state of the free particle. Okay. Now, why people actually talk about this potential and this? Because whenever we are now talking, a particle is only moving under the action of a conservative force only, there is no other force, then only you have a potential in your motion. Now, let us say I am now adding some other forces, but always one of the forces remain conservative. Then your system may or may not conserve energy, of course, but your system can be can always associate a potential, because you have one or at least one of the forces which are conservative. Okay. You can actually think of several situations, I would like to mention them here. That is, since I said that summation over I, if I should be 0 is the most general condition of equilibrium in classical mechanics, actually you can think of dividing the whole thing like summation 1 if conservatives, if I, so I should be some 1 2, I do not know like m, plus summation 2 which I call f dissipative. Okay. I is equal to 1 to some numbers. Okay. I mean I can also write j, so that this is not get confused in any case. Okay. And this should be equal to 0. So, you see that if you have some conservative force fields, and some dissipative force fields, okay, then the net effect of this can be 0. So, now you can think of different sub cases. For example, it may be possible that your system has some conservative force fields which are non-zero and some dissipative force fields which are non-zero, and they can actually negate each other to establish an equilibrium state. Now, it is also possible that there is maybe one conservative field and 2 or 3 dissipative fields which are actually negating each other vectorially. Then your system will dissipate energy, but your system will always be under non-equilibrium state, but it will not dissipate energy. Okay. Once again, so you understand, I am saying that let us say the case where your particle is undergoing the case where you have one conservative force field and 2 dissipative force field, F2 and F3. So, this is dissipative, this is dissipative. Let us say somehow I have some situation, so initially they were like that, but finally I can actually have a situation, I can somehow tune the forces a little bit from outside, and finally let us say I have made a situation where this is not 0, but this is exactly equal to F1. That means this is equal to 0 if. Okay. then again the system, although you have some dissipative forces, but the dissipative forces, they are battling with each other and they can kill each other. So, finally, the net effect will only come from conservative force field. Now, you see that is exactly the opposite case as I discussed here. So, here you had a case where the acceleration was 0, but your energy was dissipating. Now, you have a case where your acceleration cannot be made 0, but your energy is actually, and also you have some dissipative forces, but still your energy is conserved. So, those things you have to understand whenever you are encountering problems and small exercises. Okay. Some interesting exercises I can give you in the assignment. Now, why to talk about this potential and how to relate them from different types of equilibrium. So, whenever potential comes into play, then we have actually two associated terms, stable equilibrium and unstable equilibrium. Of course, there is another term, neutral equilibrium. Okay. So, in this lecture I will mainly talk about a little bit about potentials, stable equilibrium and unstable equilibrium. So, you see that we know in general that F should be 0 if F is the F net, that should be 0 for equilibrium, that is the condition we require. Okay. Now, in general that means that your gradient of phi is equal to 0. So, the gradient of this equal to 0. We can actually have some relations from that in 3D that we will do. Now, for the time being we again go to our well known one dimensional motion, where I can write that phi to be is equal to capital U, and we just have one dimension. So, we can write that equilibrium means du dx to be equal to 0 at some values of x. Let us say that value is x 0. Okay. If I have that, then I can actually, depending on the second derivatives, I can actually define two type of equilibrium. If I say that d2u dx2 at x is equal to x 0 is greater than 0, that means u was actually suffering a local minimum at x is equal to x 0, and I can also have d2u dx2 less than 0 at x is equal to x 0, that means it was suffering a maximum. So, it is a maximum at x 0 and it is minimum. So, maximum and minimum for u, okay, minimum at x is equal to x 0. If I have this, then in the first case I call this stable equilibrium. In this case we call this unstable equilibrium. Okay. Now, you see that another case is also possible, that u is throughout constant, and that is why du dx is equal to 0 at all point. Now, again I am telling that this is the case where your f is identically 0. F is identically 0 at all x, means du dx is 0 at all x. That is not an equilibrium position, that means there was nothing. So, equilibrium simply says that the interesting point is coming when in a motion of a particle, the particle is moving at different positions in space, and if the force is a function of space, that is the most often the case, okay, and then according to the space coordinates the force also changes. Now, if at some privileged or some special points, the values and the directions of those forces become such that they are balancing each other to have a net 0 force, then only we talk of a meaningful equilibrium state in classical mechanics. Okay. So, for example, now you can think simply from your experience the case of a simple pendulum. The pendulum, so it can actually start, so you can think of a bob from the very tip of this pen, and this can be thought to be a massless string. Now, you see whenever you start moving this from this point, it will come back here like this and try to come to here like this. So, you always know that this is the position of a stable equilibrium. Okay. So, now if I now ask you whether this position or this position or this position, they are equilibrium points, of course, the answer is no, because the forces are not balanced there. Okay. And only at this point the force is balanced. Okay. So, you see that, and but of course, the question you know that why then this moves, because the force is balanced does not say your velocity is 0. The force is balanced means the acceleration is 0. So, at this point you will have some non-zero velocity which can help you to move, that you know from your higher secondary courses. Okay. Now, this is the basic difference between the equilibrium point and the case of 0 force once again. So, you see that in this part of the discussion what we have actually put is the general concept of equilibrium, and a little bit that equilibrium can be associated to potentials, and then two related concepts also come. One is very important, one is stable and another is unstable. What exactly they are, then that I will be talking about in the next lecture. Okay. Thank you.